Okay, here's a shocking fact. Your computer isn't actually doing 1,000 things at once. We open 20 tabs, stream music, download a game, and chat with friends, all without a stutter. It feels like a technological miracle, like your PC has some superbrain juggling everything simultaneously. But here's the truth, that common belief, that your CPU is a massive parallel processor for every single little thing, is actually misleading. Even with multiple cores, the illusion is far more complex and clever than you might think. So, how does your single computer, with its humble CPU, manage to trick you into believing it's doing so many different tasks at the exact same moment, delivering that buttery smooth experience? What's the hidden trick, the real secret behind processing 1,000 tasks at once? Let's break down the genius of the CPU. Alright, first up, let's get crystal clear on what we're actually talking about, the CPU. We often call it the brain of the computer, and that's a pretty good analogy for general understanding. Think of it like the head chef in a busy restaurant kitchen. This chef isn't just chopping vegetables, they're reading orders, directing other cooks, timing dishes, and making sure everything goes out perfectly. But here's where the analogy gets interesting. The CPU isn't just one big, amorphous blob of processing power. It's a highly specialized component. Its core job is to execute instructions. It performs arithmetic, logical, and input-output operations. Every click, every keystroke, every pixel change on your screen starts with an instruction that goes through the CPU. It's not a storage unit, like your hard drive, which holds all your recipes. It's not a giant memory bank, like your RAM, which is the chef's short-term memory for ingredients currently in use. The CPU is purely about doing. It processes information. It makes decisions, one instruction at a time, incredibly fast. This distinction is key to understanding how it handles so many different jobs without getting bogged down. And here's where it gets interesting, the difference between concurrency and parallelism. These two terms sound similar, but they're fundamentally different, and understanding them unlocks the CPU's magic. Let's use our chef analogy again. Imagine you have just one chef in the kitchen. That chef needs to prepare a 5-course meal for one table, and a quick lunch for another, and make a dessert for a third. They can't do everything at the exact same microsecond. What they do is called concurrency. They'll chop some onions for the first course, then quickly flip the burgers for lunch, then stir the sauce for dessert, then go back to the onions. They're rapidly switching between tasks, making it appear like everything is happening at once. To the diners, their food arrives seamlessly. That's concurrency, one CPU core appearing to handle multiple tasks by rapidly switching between them. Now, imagine you have 4 chefs in that kitchen. Chef 1 works on the 5-course meal, Chef 2 handles the lunch orders, Chef 3 focuses on desserts, and Chef 4 is doing prep for tomorrow. They are all working on different tasks at the exact same time. That's parallelism. This is what happens when your CPU has multiple cores, or when a single core uses technologies like hyper-threading to run multiple threads simultaneously. Each core or thread can genuinely work on a different piece of a problem at the same time. Most modern CPUs offer both, a base of parallelism from multiple cores, with each core then handling multiple tasks concurrently. It's a powerful combination. But the genius part is this: who's telling the chef what to do next? Who's coordinating this incredible dance of tasks? That's the operating system, the OS. Think of the OS as the restaurant manager. This manager doesn't cook, but they are constantly reviewing orders, assigning tasks to chefs, timing everything, and making sure no one chef is overwhelmed or idling. In the old days, back in the 1960s, computers were more like a single-order diner. You'd give the chef one recipe, they'd cook it from start to finish, and only then would they take the next order. This was called batch processing. There was no multitasking. Then came time-sharing systems in the 1970s, which was like the manager saying, "Okay, chef, work on this dish for 30 seconds, then switch to that dish for 30 seconds, then this other one." It introduced basic concurrency. But it was with systems like Windows 95 in the 1990s that true, preemptive multitasking became commonplace. This meant the OS could force the CPU to switch tasks, even if the current one wasn't finished. It wasn't waiting for a polite pause. It was a proactive manager. Today, with modern operating systems and multi-core CPUs, the manager is a master of efficiency. They are constantly looking at all the programs you have running, all the system tasks, and deciding which one gets the CPU's attention next. This continuous decision-making, this sophisticated task management, is what we call scheduling. It's the core reason your computer feels so responsive, even when it's under heavy load. So, how does the OS actually make the CPU switch tasks? This is where the term context switching comes in, and it's where the real magic happens. Imagine our single chef, working on a complex sauce. They've got their cutting board, their whisk, their recipe open, and they're fully immersed. Suddenly, the manager, the OS, says, "Hold on. Urgent lunch order coming in. Switch to burgers now." What does the chef do? They don't just abandon the sauce. They carefully put down their whisk, close the recipe book, maybe jot down a quick note about where they left off, and then clear their workspace. That's saving the context. Then, they grab the burger ingredients, open the burger recipe, and start flipping. That's loading the new context. Once the burgers are done, or after a set amount of time, the manager might tell them to switch back to the sauce. They then save the burger context and load the sauce context. In technical terms, the CPU has a set of registers that hold important information about the task it's currently running, things like where it is in the program, what data it's currently working with. When the OS decides to switch tasks, it tells the CPU to save all that information into memory for the current task. Then, it loads the saved information for the next task into those same registers. This entire process, saving one task's state and loading another's, is called a context switch. It happens thousands, even millions of times per second, making it seem like your computer is running many applications simultaneously, even if it only has one actual CPU core. It's an incredibly fast and efficient sleight of hand. Why should we care about this complex dance of context switching and scheduling? Because it directly impacts your user experience. It's the difference between a smooth, responsive computer and one that feels sluggish and frustrating. Think about gaming. When you're playing an intense game, your CPU is constantly processing game logic, player input, enemy AI, and physics. If the OS scheduler isn't doing its job well, or if there's too much competition for CPU time, the game might stutter, frames per second, FPS, could drop, and your experience is ruined. We're talking about wanting 60 or more frames per second for smooth gaming. Or consider a professional video editor. They're rendering a complex video, which is a very CPU-intensive task. At the same time, they might want to browse the web for a quick fact or answer an email. Thanks to effective scheduling and context switching, the rendering continues in the background while the browser feels responsive in the foreground. Without it, your entire system would grind to a halt during the render, making it unusable. Even simple web browsing benefits. If your browser doesn't get enough CPU time, pages load slowly, and scrolling feels choppy. We often expect UI latency to be under 100 milliseconds for a responsive feel. Good scheduling is about fairness and efficiency. It tries to give every running program, every process, a fair share of the CPU's attention, while also prioritizing critical tasks to keep your system stable and responsive. It's why your computer doesn't freeze up when you open 50 browser tabs or start a big download. So, where do we go from here, especially with modern CPUs? The trend is clear: more cores, more threads. Instead of one superfast chef, we're getting more high-speed chefs. This means that true parallelism, where multiple tasks are genuinely processed at the exact same time, is becoming more and more common. Technologies like Intel's hyper-threading or AMD's SMT, simultaneous multi-threading, allow a single CPU core to handle two execution threads simultaneously, further enhancing that feeling of concurrency, making one physical core act like two logical ones. The operating systems are also getting smarter. Their schedulers are constantly being refined to make better, more intelligent decisions about which tasks get CPU time, and for how long. They adapt to your usage patterns, prioritizing the application you're actively using over background processes. It's even possible to run an entire operating system, like Linux, within your web browser, thanks to projects like JS Linux, which can use WebAssembly to execute x86_60-4 code. This is a powerful demonstration of how much raw processing power modern CPUs and browsers have, effectively simulating a full computer's CPU, complete with its multitasking capability.